Okay, so we are proving this equivalence of PD and CFL, and we already showed this direction that if you have a CFL, you consider a GNF grammar, and from there you can construct a PDA which simulates the derivation of this grammar. So for the other direction, we should consider any arbitrary PDA, and then we should construct a grammar which generates the same language that is accepted by this PDA, and by acceptance here we will use this empty stack criteria. So in particular we will prove this statement that if a PDA accepts a language L by empty stack, then L is a CFL. So we will construct a grammar for this L. So consider this PDA with all its components, all its 7 components. Now this sigma is the input alphabet, so this is the alphabet for your input, and we saw in the other proof where we constructed PDA from grammar, we saw that the non-terminals correspondent to the variables corresponds to the variables, right? Now in that case the state was kind of irrelevant. We just used one state and it was not used at all. But here you are starting with a given PDA with lots of states, and this transition function can be anything which changes the states as well as it manipulates the stack symbols. So the variable, it still kind of has this thing here, this gamma. So there is a correspondence between these stack symbols here and the variables in the grammar. But still this has to somehow address this switching of states. So this V is a combination of this whole thing. So it will be clear as we go through the proof why we need this triplet. But yeah, this V is a triplet. The first component is a state, the middle component is a stack symbol, and again the last component is again a state. Now this triplet we just for our convenience will write like this. So inside this third bracket we will write this as subscript, but there is no, so this is just this triplet. Okay. Now the whole motivation for considering this is again kind of make a correspondence between leftmost derivation in the grammar and the action of this PDA. Okay, we did this for the previous case also. Now here this is what we want to prove. So now this is a variable in our grammar, right? So this is what we want to prove, that this symbol will derive a string over terminals, this W, if and only if the PDA, if it starts with say this state Q, so say this Q and P are mentioned here. So if it starts with state Q and processes this W with this A as its stack string, so the stack contains only this one symbol. So if it starts from this ID, so then after some number of steps it should reach, it consumes all the symbols here, so this becomes epsilon, and after consuming this the stack becomes empty. You see that there is nothing in the stack, so this part is for the stack string, right? And the state is P. So the relevance of this Q and P here is like, it's like it starts with state Q, it somehow goes through the all its moves, and it so here for the grammar it generates W. The corresponding thing here is that it kind of consumes this W, and then it's also like processing this A, right? So this was in the stack, and after this whole path, this star means there are multiple steps here. So this whole path is about kind of consuming this A completely. So this A will be replaced by something else, so that will be replaced by something else, but at the end everything will be consumed, and everything originated from this capital A. So all of those things will be consumed, and you will be left with nothing in the stack here. And so when you are completely done with this A, that means you have in this process consumed W and you ended up in P. So this is the state where you start, and this is the state where you end up. So that is the intended significance of this Q and P before and after this thing. Okay, so this is what we will prove, and our construction is motivated by this. So this is what we want to do. So accordingly we will define this thing, but obviously the proof will be written in the other way. So you have to first define this grammar, and then you show that this claim holds in your grammar. But the definition doesn't just fall from the sky. So the motivation of defining this start symbol and all these productions, so the whole motivation comes from the fact that this is what we want to have in our grammar. Okay. So now, even before I'm describing what these things are, so if this is true, if this claim is true, how does that imply that the language is same? So that means the language generated by this grammar G is same as the language accepted by this PDA M by empty stack. So that is why it's N of M. So how does this happen, and from this how does this follow from this claim? So that's easy, because so the starting thing is this. So this is one production that we will have in our grammar, and this is the start symbol in our grammar. So see, this is the start symbol. So the first thing will be a step like this, a single step, right? And then so after some number of steps, it will derive this W, and this happens. So since we will prove this claim, we haven't proved it yet, but once we prove this, this will mean that this ID, okay, so it directly comes from here. So from this ID we can go to this ID. And what does this mean? This means that the input is completely consumed. So this was and the stack is empty, and this is the start state of the PDA, right? So this is the very first ID of this PDA. So that means we can derive this string W from S in our grammar if and only if this W is accepted via empty stack in M, right? And this if and only if ensures that these two languages are same. So that means it's sufficient to prove just this claim. As a corollary, we have this thing that we are trying to prove here, right? So now we haven't even discussed the definition. So one thing is this, that this A goes to this thing, and again the motivation, as I said, is this, because initially the stack will contain just Z0, and the Z0 will go to empty. The string will go to empty from Z0, starting from this state Q0, which is the start state of this thing, but ending in any state, because since we are just considering this empty stack criteria, this can be anything. In fact, here it should be 5. because for PDS where we use empty stack, we generally put this as 5. We can put some f here, but that doesn't matter. So you can just consider this as 5. So this was we have already discussed the motivation for defining this. Now what about this transition? See, what is happening here, that if this pair is in this QAA, that means you are in state Q and you are processing this input symbol A, right? And you are looking at the stack symbol capital A, and then the state is changed into this Q1, and this instead of A you will have this bunch of symbols here. Now just compare it to this claim. So from here we want to go to the empty stack, but this will not give you an empty stack, so this will replace this A by some other bunch of variables, and again you have to expand these variables in order to get some terminals, and in that process you will just remove this thing from your stack. But in that process you will go through some input symbol, right? So in grammar you are generating that thing, in the PDA you are consuming that thing, that same. But that means from here, so this whole process starts with this state Q, and you are looking at this thing, and once you are done with this A, means you cannot leave it to just this B's and all, so you have to go to this empty stack, right? So that means you have to take care of each of these B's also. You have to process all the input symbols, which kind of removes this B's from the stack. And in that process, so after this one step you are in Q1, and after you clear this B1, and this clearing this B1 will not happen in single step, right? Because this is what we are talking about. Clearing means whatever is generated from this B1. So this B1 can again expand into some, say, C1, D1, whatever. So, but everything has to eventually go, and you should arrive at this B2. And at this point, suppose the state is Q2. Okay. So then from Q1 you will go to Q2 where you have processed this B1. Then again from Q2 you have to go to you will go to some Q3 where you have processed this B2. And each of this processing itself will involve many steps, right? Because this B2 can expand into something, and then eventually that will get consumed and those kind of things. So after all these things you will arrive at this Qm plus 1. So that means starting from here, first you consume this A, and then you have to take care of all this B's, and after that you will go to this Qm plus 1 in your PDA. So that amounts to this thing, that you start from Q and you completely take care of A, and you arrive at Qm plus 1 where you have converted this A completely into terminals. So this is the motivation. So this is not a proof at all. This is the motivation behind defining this thing, and the motivation came from the fact that we want to prove this thing, and this is sufficient to prove this thing, right? Okay, now let's actually prove that with our definition this claim actually holds. Now we have to show that our motivation actually works. Now before doing that, so how do we prove again that same trick, doing some induction, and we are doing induction on the number of derivations and number of this this transition in PDA. So we will break it down into two steps, since there is a if and only if. First we prove that if this happens, then this happens, then we prove that if this happens, then this happens, and in each case we take the number of steps required here and here. If that is I, we do induction on I, and the basis is I equal to 1. So because we cannot take a basis I equal to 0, because you see that this part is empty, right? So this is the stack part which is empty. So if I take I equal to 0, then these two sides will be same, right? And we cannot start with empty stack. So we already have a variable. So in both cases we already have a variable. So we are starting with at least not at least, I mean exactly this one symbol in our stack. So here we cannot just take I equal to 0, because this has, in our theorem, this is epsilon. So our basis starts at I equal to 1. So that means in single step we should go to empty stack. And when can this happen? When can this happen? So this means that so so this means that this goes to just the single symbol. Okay. Why? This comes from our definition here, right? So what are we trying to prove? We are trying to prove this statement, right? For this single step process, right? Now this in single step goes to some string. When can this happen? If this part in the single step, so what are the productions here? I mean, this production are also in GNF format, you see, except for this thing. This starts goes here. So except for this first step, all these productions are sort of this GNF. So we have a symbol here, and rest are variables, right? Now in single step, that means we are just using one production. This can go to a string if that string is just this symbol and there is no variables after that. Okay. So this can happen if I only have some production like this. So this part is just empty, right? So that means what sort of transitions we are talking about? So this so this part is empty. So yeah, so this part will be empty, right? So from here, if you compare with this thing, so there is no B's at all. So for this I equal to 1, this is a single step process, and correspondingly this will be the transition. And if this is the transition, then this is one transtile, this one transtile step, which goes from here to here, and everything checks out, right? So this is the basis I equal to 1. Now for I more than 1, let's see what happens. So yeah, we have defined this thing, and we want to just prove this claim. So again, as I said, and we will break this down into 2 steps. First, this implies this, and this implies this. So let's first prove this one. Okay, that in I many steps, if the PDA accepts some W, then that W is generated in our grammar. Okay, so here we have this M, and here we have this G. Okay. Well, now this W, let's say the first symbol is A. Okay. So the first symbol is A, that means since the okay, so that means from here to here we have a transition of this form, right? So it has to consume this symbol A, because that's the first input symbol here, and the top stack symbol is A. So that means, and the state is Q. So from state Q, it is seeing this input symbol A and this stack symbol capital A, and from there it is going to some Q1 and some stack string. So this A will be replaced by some bunch of variables, stack symbols. Okay. So this is the first step that it has to make. Okay. So then what are this x1, xm, and so on? So these are also part of this W, but which part? So see, from here, so this is the stack now, right? So this A was replaced by this because of this. Okay. Now after some point of time, this A1 has to go, right? So this A1 can be replaced by something, some B's, some C's, some D's, whatever. So you can have all sorts of jugglery here, but at some point of time, all this thing has to wrap up, and finally you have to come to this A2 at this point, right? Because eventually you are going to the empty stack. So one by one, each of these symbols has to go down. So you have to, the stack goes down in length starting from here. But after some number of steps, in the middle you can have arbitrary sort of lengthening and shortening, okay, of the stacks. So now this x1 is the part which is consumed. So this is the part of the input which is consumed in the process that starting from this stack string, it goes to this. That means it has completely processed this A1. So in doing so, it consumed this A1. So that is the part of W that I write as x1. So similarly, from here to here, it will take some more input symbol. So that part I call as x2, and so on. So it has to finally take care of all this m many symbols here, and correspondingly we'll have this m many parts after this A. So this W looks like this, and this is what happens. And this qm plus 1 is actually P, because from here we are saying that we are going to this P. And if we add all this up, so this 1 plus I1, I2 up to Im, so if I add all this up, that is I, right? So that means each of this I1, I2, I3, etc. So they are obviously strictly less than I, right? So if that is the case, now we can employ now we can employ this claim, so as induction hypothesis, right? Because we are using this induction hypothesis for these steps, this I1 many steps, I2 many steps, which are less than I. So by induction we can do that. So but the claim is for this format. You see, you have a single variable here, and you have an empty stack here, which is not the case here. So you have some stack symbol here, and then again some stack symbol here. But that is easy, because if you consider the steps from here to here, so all that is happening is beyond this A2, right? This A1 is being replaced by something else, that is being replaced by something else. So from this A1 you will have some growth in the stack, and it will grow, shrink, grow, shrink many times maybe, and finally it comes to this thing. So this amounts to the fact that if I had just this A1 here, so if I just had this A1 here, so from this step, from this ID to this ID, the same thing will work for this this PDA, where we just do not have this A2 up to AM. So that means if we started with just this A1 here, this A1 will grow and shrink accordingly, what happens here, and where this is completely consumed. So in this case, this means that the stack becomes empty. So instead of this stack string, so what I'm saying is that in our PDA, instead of this stack string, if I just started with this one stack symbol that and here it's the same thing. So the same steps will can be carried out with this ID, and when this is finally removed, that amounts to the fact that here the stack will become empty and it will go to this Q2, right? So this is a crucial step that you need to understand. So if you do not understand, just pause the video and try to just understand this thing, that we can, if we have this thing, then we can remove this thing and claim that this is also true. Okay, just think for a moment and it will seem trivial, but trivial or not, this is the crucial step of the proof. Okay, so if you are comfortable with that, so the same thing happens here. So from here to here, it is just consuming this A2, and it doesn't even do anything to this part. Okay, in this steps, in this I too many steps from here to here. So again, here we can just assume that if we just had this A2 here and with this Q2 and it consumes this X2. Okay, the same applies for this thing also. So we can assume that this is not even there. So all that is happening is it is consuming this input symbols which is contained in X1, and it is consuming this A1, and it is going to Q2. And similarly here what is happening is it is consuming this X2, and it is consuming this A2, and it is going to Q3. So this is what is happening here. It is consuming X2, A2, and it is going to this thing. So yeah, so this transition is equivalent to this transition, and this transition is equivalent to this transition. Okay, so once we have this form, we have this equivalent statements for all these transitions. Now we can employ this claim with as a induction hypothesis, because as I said, this I1, I2, I3s are less than I. So what will we have from here? So this will mean that yeah, so from starting from this say Qj, we can go to Qj plus 1, where we are processing this Aj, and in this process we are generating this Xj, because that is what is consumed here, right? So for this A2 we are consuming X2, for A1 we are consuming X1. So that means from this so from this claim. Okay, just compare this with this. So it's just a direct application of this. So we are generating this Xj's from these symbols, right? And this tells us that, so now by our definition here, we have this pair in this transition function. So if we have production like this, I mean, we design our grammar with this sort of productions. So what we will have is this step, right? Because from here to here, this will be a production in our grammar by the definition of our grammar, right? And this happens because this happened in our PDA. So from here we can go to here, and then from each of this part we have already proved that we can generate this Xj's, right? So after this A, we will have this X1, X2 up to Xm for each of this part. Okay, you can consider a leftmost derivation, so that you first get Ax1 and then Ax1, X2, then Ax1, X2, X3, so on, and finally you get this thing as a leftmost derivation. So this is actually a leftmost derivation. Okay, where the first thing comes from our definition here, because we have this transition function, and the rest we just proved here. Okay. So you see that this actually, so this is what we have. So now this is one direction. The other direction is almost same. You just I mean state the same argument just in the reverse order. So instead of starting with this PDA and showing this that you can derive this in the grammar, we start with the fact that we can derive that with in the grammar, and then we show that we can accept that with the PDA. So for the other direction where we are accepting this string, where we are generating this string from this variable. So when can this happen? Again, we can break this W as this a x1 up to xm, and what is the meaning of this x1 up this xj and a, because all the productions are of this form. So when we are expanding this thing, the first thing will be some symbol. So this is the first symbol, and then you will have a bunch of variables. Okay, and for each of these variables we have this x's. So for the ith variable here we have this xi, so that yeah, this happens. So yeah, this is the meaning. Okay, so if I have a qj aj qj plus 1, so then in some ij many steps we derive actually xj. So if I put everything together, this becomes this x1 up to xm with this a here. So this whole thing is our w, right? And so by induction hypothesis, now we are going from here to here. So now so first of all, this says that so this is not my induction hypothesis. So this the induction hypothesis applies for from here to here. So this comes from the fact that we had this in our grammar. So that means we have a production of this form in our grammar, and we can have a production of this form in our grammar if and only if we have a transition function like this, right? So we have a transition like this in our PDA. So from this from this ID we can go to this. Why? Because this is saying that you are just replacing this top stack symbol A with A1 up to AM, and you are going from state Q to Q1, and in the process you are just consuming this terminal A, right? So it is just consuming this terminal A. So it is left with the rest of the part. The state is changed from Q to Q1, and this A is expanded into this whole thing. Okay, this is fine. And from here, as I said, by induction hypothesis for all these steps, now we have so yeah, so we have all this thing, that from Q1 if you process say this x1, and that means you will completely also process this A1 which is at the top, if it is at the top, and then it will be completely consumed. That means this A1 is completely consumed. You will be left with nothing, right? And in that process you will also consume this x1, because this will also become epsilon. And similarly, it happens for all xj's. And now the argument goes in the other direction, that this happens if and only if this happens, because this is same as saying this, right? from here to here you can go, if and only if you can go from here to here. So it says that if you start with Q1 and if you are just processing X1, so in that process you completely consume this A1, and yeah, so that is what it says. It doesn't matter. So in this case, it won't. For this many steps, it doesn't do anything with this part of the input, and it doesn't do anything with this part of the stack, right? So it doesn't matter what is here. It just looks into this part and this part. So yeah. So from here we can now go to this direction, and this means that from here we can go to this empty stack where we have consumed all the input symbols, and we are left with this Qm plus 1, which is P. So yeah, so this Qm plus 1 is P. This whole thing, this A1 up to A1, sorry, AX1 up to XM, that is W. So yeah, we have proved this statement here. So this concludes the proof that PDA and CFLs are same. So now this is the moment where we got the first hierarchical relation between this regular and CFLs. So not yet, we have to give another. So you remember in the Chomsky hierarchy we said that we have this RE languages, this set of RE languages, not sorry RE, this regular languages, and the CFLs are a superset of this thing. Okay. The CFLs are superset of this thing, and this regular languages, so they correspond to, so from the automata perspective, so it's like you are considering languages which are recognized by finite automata, okay, and then you are considering a superset which is recognized by PDA, right? So this is PDA. So the sets that I am showing, it's the set of languages. Okay. So for formal language L, what we proved that L is accepted by a PDA by final state if and only if L is accepted by PDA by empty stack, that we proved in the previous thing. And then we proved that L is accepted by a PDA by empty stack if and only if it is a CFL. So now we can put these two together and we can say that L is accepted by a PDA by final state if and only if L is a CFL. Okay, we can go from here to here. And once we have this statement, it becomes clear why this is true, because now the PDA is actually PDA accepting language by final state. So that is a generalization of finite automata. Why? Because in finite automata you also have this states, this input alphabet, the start state, final state. So those are same in here. So if you consider a corresponding PDA, you have the same Q and sigma and Q0 and F. And you can have you can simulate the transition of this DFA here also, because in the DFA if you have say this thing, that from Q upon seeing this symbol A, it moves to P. So you can also have that behavior in your PDA. So if you are in state Q, if you see A, then you move to P, okay. But then you also have to address this stack symbol, but since we are just simulating this M, we do nothing to the stack symbol. So this, it starts with this Z0, we have a Z0, we have to have a Z0 here, But we do not have any other stack symbol here, you see. We just have this Z0 because we cannot remove that. So it starts with this Z0, and in each of this transition it doesn't do anything to the Z0. Z0 is just being replaced by Z0. So the stack is always just Z0. Okay. And also in PDA it is defined as a kind of non-deterministic machine. So we have to have a set here, but here we can just have a singleton set. So it kind of deterministic transition here. So this is the transition in the given DFA M, and then in the PDA we are mimicking this transition of states using this, where we are doing nothing to the stack. Okay. So if I do this thing and then if I employ acceptance by final state, so then it becomes exactly equal to this M, right? So once you reach P which is in F, so then you accept string, the input symbols that you have already consumed. So the same thing happens here. So here it's very easy to see that PDA with this final state acceptance criteria is just a generalization of this finite automata. Instead of DFA, I could have taken NFA with epsilon transition, because that are already inbuilt in this PDA definition. But anyway, DFA will make it simpler. But yeah, so the extra power that the PDA has is just manipulating the stack. Okay. So you see that in this case the language accepted by the DFA is the same as language accepted by PDA. So this shows that any FA can be simulated by a PDA. That means any regular language can also be accepted by a PDA. And since language accepted by PDA is essentially context-free language, so this means that every regular language is a CFL. So so up to this point, so this what this is saying is that so take any DFA M and then we can construct a PDA P such that the language accepted by this DFA M is the language accepted by this P by final stack, by final state. So this thing, what this thing is saying is that every regular language is a CFL, right? So this says that every regular language can be accepted by a PDA by final state, and then combining with this, that L is accepted by a PDA by final state if and only if it is a CFL. These two together means that every regular language is a CFL. So we have this hierarchy. Okay. But the converse is not true, right? Because we know that this is a context-free language, right? You can easily write a grammar for this. We have used this example many times for describing CFLs, right? So this is a CFL. But if you remember what we did in pumping lemma for regular language, this was a prime example there where we showed that this language is not a regular language. So we used pumping lemma to prove that this language is not a regular language. So we have a language which is a CFL but which is not a regular language, and we have the proof that all the regular languages are also CFLs. So that means this inclusion is strict, right? So this is a strict subset of this CFL. So this is the regular language. So these regular languages are strict subset of this context-free languages. So whether you consider the model of computation as grammar or this push-down automata, so these models are strictly more powerful than this model of finite automata. Here, this whatever you consider deterministic, non-deterministic, here everything is equivalent for finite automata. But this model that we are considering, PDA or grammar, this context free grammar. So this is strictly more powerful than this finite automata. Okay, so that's it.